This is the fourth lecture in the series, and we have two more in the end of the academic year. Welcome you all from here at Harvard, and also the people online from NIR Consortium and elsewhere. I'm delighted and honored to have Bob Hart from Brown University with us today. We know Bob for quite some time. He's also a member of the external advisory board for the Nanosafety Center, so we value his input in all research we're doing in the center. So I will keep my introductions short. So he's well known in the community. Just to say a few things, he's also an editor-in-chief for Carbon. He established, he's a founding director, actually, of Brown's Materials and Nanoscience Institute. He's a prolific writer, of course, tons of publications. And the topic, actually, it's an exciting topic, both in terms of applications, but also in terms of the implications. It brings on the table an emerging class of inorganic based materials. Is that they go with how we characterize them, how we understand their behavior in biological media, which is not trivial. I mean, we just started studying these materials in the consortium, and even how to handle them in biological studies and toxicological studies is quite a challenge. So we are excited having you here, Bob. I know you've been working in this area for quite some time, so we are looking forward to your presentation and share your experiences with us. So welcome again, and thanks for taking the time and visiting us.
To visit the Harvard School of Public Health on this beautiful day in Boston as the nor'easter bears down on us. I'm a little envious of the people who are watching this by webinar who don't have to go home to Providence tonight. And if it doesn't work well, though, Phil, you have to put me up in a hotel tonight, so keep that in mind. So I've been working in the sort of nanosafety area for well over a decade, and most of my work is done in close collaboration with the group of Agnes Kane in the Department of Pathology and Laboratory Medicine at Brown. And and like Phil's center, much of our work has been funded by the NIEHS, and we're very grateful for that. Our recent interest has been in sort of two-dimensional materials, and this field really took off, as I'm sure you know, in 2004 with the discovery of graphene, its isolation using the Scotch tape method, and its characterization, which led to the Nobel Prize in 2010. And there's been just an enormous amount of work on graphene, and it's shifted from work on fundamental electronic properties to applications over, say, the past 5 years. And in parallel with that work on applications, of course, must come work on the development of large-scale synthesis methods, ways of nano-manufacturing graphene. And so here we are in 2018, and what we have as a result of that effort is a sort of a family of what I call graphene-based materials. These are materials that are not just the ideal pristine monolayer that you see on the cover of Nature, but a few layered materials, many layered materials, materials with highly altered surface chemistries. And some of a bulk chemical or thermal method in which powdered graphite, which can be mined for, say, $1 a pound, is exploded into individual little layer packets by bulk processes involving powders often, and are incorporated into composites and other devices and applications. And in our environmental health and nanosafety community, I would argue that this is the type of graphene material that we should be most concerned about. This is where the large exposures for human health and the environment will occur, and will be kind of the main focus of my talk. So graphene is new, mostly, but it's also old. It was first defined as a term by Hans-Peter Bohm, and at least back in 1986, who defined it as the hypothetical end member of the polyaromatic hydrocarbon series, benzene, naphthalene, phenanthrene, etc., up to graphene. Ene means the carbon-carbon double bond, and graph, Phil will know this, it's from the Greek word to write. But graphene is older still, and I kind of like this cave drawing from the Chauvet Cave in southern France. And archaeologists have taken these drawings and taken the deposits, which you see here on the left, and kind of analyzed them and dated them to, say, 30,000 years. And when I look at this drawing, it strikes me two things. One is the amazing artistry of these ancient Europeans. What a beautiful set of images, and people use charcoal even today for some artistic renderings. And the second thing is how close this work is to the Nobel Prize work that happened 30,000 years later. So this is charcoal, likely from a campfire, that was mechanically exfoliated onto these cave surfaces. And as a journal editor, I was thinking, if they had submitted this for publication, what would the abstract be? So I took the liberty of writing an abstract for this work. It's here we report that organic matter in the form of wood can be transformed by heating into solid elemental carbon and mechanically exfoliated into highly stable, optically absorbing thin films that we propose to call multi-layer graphene. I don't know if these ancient Europeans were so erudite to have done this. I haven't seen this published. Either they didn't submit it or it wasn't accepted. So it took 30,000 years to get to where we are in the world of graphene. But what's interesting is they looked around nature for a naturally occurring layered mineral. And after 2004, scientists became very inspired to go back and look to nature for other layered materials that could be exfoliated into nanosheets. And that's led to where we are today, 2018, where we have this subfield of nanoscience, which is two-dimensional materials. And now it's not just graphene, it's about a broad class of high aspect ratio, plate-like, meaning stiff, or sheet-like, meaning flexible materials. They can be monolayers, they can be few layers, they can be so-called nanoplates that are of many layers and are stiff, up to, say, 100 layers. And all of these materials are ultra-thin, and if their thickness is less than 100 nanometers, they would be formally classified as nanomaterials, which they are. And they can be fabricated by exfoliation of natural bulk materials. As we see here, here's hexagonal boron nitride on the left, which is a true single atom thick monolayer material. There it's shown as a bilayer structure. And on the right is molybdenum disulfide, in which the individual monolayers themselves consist of covalently bonded atoms with 3 atomic layers, sulfur, molybdenum, sulfur, separated by these van der Waals gaps. And you can mechanically exfoliate these layered materials using shear forces to rip them apart into nanosheets, or you can chemically exfoliate them, typically by inserting a chemical agent in between the layers, decomposing that agent, producing gas, and creating pressure that blows apart these structures into nanosheets. But in today's world, you can also grow 2D materials by CVD methods. You can grow them colloidally in water phases, and you can grow them solvothermally, so in autoclaves with organic solvents and high temperatures. These are bottom-up methods. The middle category are top-down methods to produce 2D materials. And we're in the EHS nanosafety field, and so we took an interest in this class of materials, which is a fascinating new development, I think. And we wrote a review article in Chemical Society Reviews 2 years ago, and one of our co-authors was an expert in 2D material synthesis. That's Christy Koski. You see her name in the co-author list. And she had been compiling, as a sort of hobby, a list of all the materials she knew that existed in either a nanosheet or in layered form. And that's this daunting list of chemicals you see on the left-hand side. And so we've got all this chemical diversity in this material family, but it's also crossed with this morphological diversity. If you look at the 3D plot on the right, we have chemically diverse materials, but they also vary in terms of their layer thickness from monolayers to few layers, all the way up to bulk materials. And then in lateral dimension, we have some materials that are nanoscale in the lateral dimension, and these may, in biological systems, behave in a way that's not dissimilar to particles, but then they can be grown all the way out to microscale dimensions, and these are materials with enormous aspect ratios that are rare in nature, and we can expect some unique biological interactions from. Now, how do we, as a nanosafety community, do our work to try to manage the safe development of all of these complicated materials? And that's not a new problem. It's kind of a microcosm of the larger nanosafety problem, where all nanomaterials, with their even greater degree of diversity in shape and size and chemistry, we have to somehow ensure that those go forward in a way that protects human health. And it's not unlike the larger problem in chemicals. So even with well-defined molecular structures, our synthetic powers nowadays are such we can produce so many more chemicals than we can test by traditional methods. So we all know this. And it's led to an interest, certainly for my case, in sort of generalizable methods to look at families of materials and help us make progress in chipping away at the safe development and safe design of a family of materials like emerging 2Ds. So as part of our article in 2016, we sort of laid out this framework, and you can see it's from a material scientist's perspective. It's a framework for understanding how a material may interact at the fundamental level with biological molecules and cellular substructures. And so we kind of identified these classes of interaction, like surface redox interactions, which is an old paradigm associated from the air pollution literature primarily, connected to the production of free radicals through surface reactions on material surfaces, to chemical interactions that involve oxidation or reduction, degradation of materials, their dissolution and the release of the soluble fragments that affect the biological system, and then finally physical and mechanical interactions. And this last one is arguably the most fundamental and the deepest problem in the 2D material field, because this is the feature that all 2D materials have in common, is this enormous aspect ratio and potentially atomically thin nature. And how do biological systems, cells, organelles, tissues, behave and respond to such unusually shaped materials? My talk today touches on each one of these areas briefly, and I'd like to start with the electronic and surface redox interactions. This is an old paradigm. Nanomaterials produce ROS on their surfaces, leads to oxidative stress. There's not been many attempts to look at this in a generalized way. Andre Nell has a theory that he's been working on, which describes a biological redox potential range. This is a sort of an electron energy that exists inside of cells and associated with the passing of electrons back and forth between biological redox couples. And this is for semiconductors. And if you take the valence band for semiconductors and the conduction band, and if you look at the location of those allowed energy levels relative to this biological redox potential range, you can identify some materials that will either accept or give up electrons at the same energy level, and thus they can participate in permissive electron transfers and interrupt the natural cellular redox processes. And this particular case shows a material with a conduction band, which would normally be empty, but has allowed energy levels, electron energy levels, in the same range, and could then therefore interrupt and be redox active in a biological system. And you can plot these for 2D materials. This is in the review article. And so these are a whole set of two-dimensional materials that we could find data on. These are the electron energies in the same format as used in the Nell theory. And you see this is the conduction band up here. This is the valence band, and the white space in the middle is the band gap. And so you see materials whose the bottom of their conduction band, and most 2D materials are in fact semiconductors, overlap this biological redox potential range and would be, in principle, be predicted by this theory to be biologically redox active. There's a set of these. And now this is a complicated field, but at some crude level, it certainly works, because if you look at HBN, it's a wide bandgap semiconductor. There's a huge gap here where there's no allowed electron energy levels, nothing that comes close to overlapping with the cellular redox range. And in fact, in most data, people do not see HBN as being redox active. You compare that to another common nanomaterial like molybdenum disulfide. And molybdenum disulfide, if I have my cursor in the right place, right here, its conduction band edge dips into this redox potential, and it would be predicted to accept and return electrons in biological systems. And the data I've seen do confirm that. So our lab is not working on this, but it's kind of the beginnings of what could be, after further development, a generalizable approach to understand the redox activity of 2D materials. Now, what we are working on, and what I want to talk about today in some length, are these chemical interactions. And this is an interesting area. A toxicologist is normally concerned with, if I introduce a material into a biological system, how the biological system is affected. But our interest as materials people is how the biological system may affect the material. And in fact, these are non-equilibrium structures. You put them into these environments, and they're capable of a variety of chemical interactions induced by the biological medium. An example would be dissolution. The biological environment causes material degradation to produce soluble products. Those products then come back and interact with the biological system. And there's kind of a bidirectional dance, if you will, a chemical evolution of a system plus its material component together that are responsible for some toxicity pathways. And we know from about a decade of work, a lot of it's on the environmental interactions of nanomaterials about these transformations. And most synthetic nanomaterials are believed by their producers to be stable. One doesn't make unstable materials because they can't be used for anything, but they're stable under the conditions they're formed, and they may be stable on the bench at room temperature. But if you take them out of that environment and you put them in ultra-dilute conditions, in media with reducing agents and with oxygen, which is ubiquitous in biology, you get transformations that include dissolution, degradation, sometimes phase transformations. And there's a kind of a large literature that is developed on this. And our particular interest today is in dissolution and degradation phenomena. And we've seized on this as something we want to look at for 2D materials because it has really important implications. First, it determines whether materials are persistent. And for solids in the human body and in the environment, persistence is arguably the most important property you might want to look at for evaluating the risk of a toxicant in the environment of the human body. And secondly, this dissolution phenomena is very important for understanding the toxicity mechanism. In dissolution scenarios, one is exposed both to the particle and to the soluble ions. And a classic example is silver. And about a decade's worth of work on silver over the last period has shown that most of the biological effects associated with silver nanoparticles are really due to the ion. And you cannot understand the data or behavior on silver unless you understand that the particle is really an inventory, a high-density collection of atoms waiting to be oxidized and dissolved to produce the bioavailable and bioactive silver ion, which is the actual toxicant. And so we had the idea that these dissolution phenomena would be particularly important for 2D materials. And so we set out in our review article to do some kind of screening to start. And this is our review article team. There's Agnes Kane and Huajing Gao, who you'll see later in the talk. And so we gathered up material data on layered materials and began to see which one of these materials ought to be stable in a biological environment or an environmental setting. And you can start by looking at simple non-redox dissolution processes. And here's a range of 2D materials on the bottom. Here's their published solubilities. And these are for the bulk counterparts where there's data available. And most of them are poorly soluble or insoluble. But you know what people call poorly soluble often are materials that are in equilibrium with a pool of ions whose concentration may be low, but is certainly in the range relevant for potential toxicity in the body or the environment. So we in the world of toxicology, we dilute systems massively. And when we dilute them, we allow dissolution processes to occur, and we get biological effects associated with materials that people think of as insoluble. So these materials are all potentially biologically active through the ion pools that will coexist with them. There's some other 2D materials like molybdenum disulfide and manganese dioxide that are extremely insoluble. So here, we have materials that maybe we should look at the solid phase very carefully and understand its properties as the ones that will govern the behavior of these materials in biological systems, you might think. But in fact, this is only one mode, simple non-redox dissolution. We also have oxidative dissolution. And many of our nanoparticles follow this paradigm: copper, silver, even nickel. And here you're plotting, this is a kind of an in silico screening method where you're plotting the oxidation potential of the material for this range of materials that we're looking at. And what you do, I can't explain this in detail, but you compare the oxidation potential of the material to a redox couple. And this is oxygen water, which is always present in our systems. And the ones that fall below that line are thermodynamically potentially oxidizable. And that's true for molybdenum disulfide. It's true for the whole class of transition metal dichalcogenides, the so-called TMDs. This is the most important class of material after graphene, I would say, in the 2D material world. They're highly insoluble, but they're all potentially oxidizable. It's not clear that they're stable. Now, manganese dioxide, we still have that. That one is predicted to stay around as a solid, you would think. But if you look at its chemistry, it's subject to reductive dissolution. And so this is the cellular redox potential concept that we borrowed from Andre. But if you imagine this expresses the electron energy in a biological system, and now we're plotting the electrochemical reduction potential of different materials, and we're comparing them to this redox potential band. And the materials that fall in or above that band are thermodynamically reducible under these standard conditions. And this redox band comes from a set of 12 different important biological redox couples. We don't have to go into the details. But it's driven by the antioxidants that are present, like ascorbic acid and glutathione and other molecules. And here we go. There's manganese dioxide. It's extremely susceptible to reductive dissolution. So when we finished this in silico data mining exercise, we had the idea that most of these 2D materials would not be stable, not thermodynamically, but kinetics mattered. So what we need were data. And so we set out, after the article was published, we actually had some data in this article, and Kem Sak Rev said, you're not allowed to put original data in our review articles. So we pulled them all out. But of course, we had another paper then, right? And so we've done a case study experimentally on some materials following this different paradigm to begin to see which 2D materials are going to be persistent. And this is my first case study. And it's Christy Koski is a nanosynthesis expert, and she makes these 2D molybdenum trioxide nanoribbons in her lab. We lost her. She's now at the UCal Davis. And these nanoribbons are neat. They are truly 2D materials in that they have layered crystal structures, and you can exfoliate them down to monolayers. But they also tend to be long and thin. So I like to say they have a kind of a dual 2D, 1D nature. If you just look at them casually, you might miss the 2D part, but you'll certainly see the one-dimensional nature they have. And they're remarkably similar in dimensions and size and stiffness to asbestos fibers. And so knowing what we know about biology, while these are 2D materials, we might want to take a special look at whether their fibrous nature would cause them to induce fiber-like health effects in biological systems. So the first thing we asked Christy when she told us about these was, are these materials stable in water? She said, oh, of course, I make them in water. I make them colloidally in water, I store them in water, and I'm going to give you to them in a stable aqueous stock solution. So we're like, great. Thank you, Christy. And we took these materials and worked with them. And this is Evan Gray, a postdoc in my lab, and Cynthia Browning is a postdoc in Agnes's lab. And we found out they were stable in sort of nanopure water. They formed this cloudy, sort of milky suspension. But in some other media, like phosphate buffered saline, they seemed to clear in a pretty short time. And we did a bunch of DLS screening and eventually did this ICP measurement. Incubate the nanoribbons in the medium of choice. We remove the solids by centrifugal ultrafiltration, and we assay the supernatant for, in this case, molybdenum as a marker for the presence of dissolved molybdenum trioxide. And what you see is some media, like this is a phagolysosomal simulant fluid, so it's a fluid that is meant to mimic the inside of a macrophage in the phagolysosome. This is nanopure water. They're stable in those media, but they're not stable in cell culture medium. And in simulated lung fluid and even EPA moderately hard water, which is an environmental simulant, they're very unstable. They disappear pretty quickly. And so we took a look at why this was, and of course it has to do with the basic dissolution stoichiometry. So molybdenum trioxide is hydrated by water, produces molybdate and protons. And of course, if in nanopure water you produce enough protons to drop the pH, and you get an equilibrium situation where the dissolution stops, which is why Christie's stock solutions are stable. And in a lot of other media, you see stability. But in buffered media, we always use buffered media, right? You absorb those protons, you allow this reaction to go further to the left, and you get dissolution. And so our combination in our field of dilution plus the use of buffers renders a lot of these materials quite soluble that would be listed normally as poorly soluble or insoluble. And that's the case with molybdenum trioxide. It's asbestos-like, but it dissolves over some time frame. But it's about the same time frame as required for cell uptake. So whether or not it can have a fiber-like effect on cells is still of interest. And this is a kind of a morphology diagram, starting with the nanoribbons at the beginning, and then in DI water, where we see no change really over the entire course of the experiment. In EPA moderately hard freshwater, an environmental simulant, we see the gradual dissolution of these ribbons. And that's because this water has calcium and magnesium in it, which provides some buffering capacity and prevent it from reaching equilibrium. PBS dissolves well. And these are kind of cellular experiments. And you can see the nanoribbons in the extracellular space, and you can see them disappearing over time. Some of them survive long enough to be taken up into cells. You can see them inside cells. This is live cell imaging from Agnes Kane's lab. And inside the cell, at the low pH in the vesicles, we see a slowed rate of dissolution, but they nevertheless do dissolve. And these materials do not elicit any adverse biological effects that we can see. They're fiber-like, but they're dissolving at the same time they're being taken up. And this is a class of material, because of its solubility in these media and the rate of that solubility and the fact that the dissolution products have a low toxicity, that we would like to select from the set of 2D materials and place in a lower priority level for further consideration. I think we're supposed to wait. Okay, so that's my first case study, and this is a material I think we could eliminate from our detailed nanotoxicology studies. The other one we looked at is molybdenum disulfide. Now, this is a very important material. It's widely reported to be environmentally stable. You can find it all over the literature. And a little wrinkle with this material is that if you mechanically exfoliate it, you get semiconducting nanosheets. Whereas if you chemically exfoliate it, you get actually metallic, a mixture of metallic and semiconducting nanosheets. And you can tell the difference. And the composition is the same, but the sulfur plane glides and changes the crystal orientation. And one's metallic and one's semiconducting. And if you take this, the metallic sheets, though, and you dilute them into an aqueous buffer, here's the dissolved molybdenum as a function of time. You see a slow increase in that molybdenum. And it starts to approach the total molybdenum concentration of 8.4 ppm. Now, this is a very slow process. This is 100 days. So if you're very patient, this material will go into solution, the pH dropping. And if you do the whole thing in deoxygenated water, you see a much lower rate. And this is likely just due to residual oxygen in the sample. So this is, according to our prediction as well, an oxygen-mediated oxidative dissolution of molybdenum disulfide. It's slow. It requires aqueous phases. It requires dilute conditions, but it's real. And it would very likely render this material non-persistent. And it produces molybdate and, of course, protons. Now, so the dissolution rate turns out to be pH dependent. It's actually slower at high pH. It's slower at low pH. It's faster at high pH, which is the inverse of some systems. But what's really neat is that the chemically exfoliated material oxidizes and dissolves much faster than the mechanically exfoliated material. Why is that? Well, one idea would be that it really depends on phase, that the metal oxidizes faster than the semiconductor. And this is XPS data. And the original chemically exfoliated material can be deconvoluted into a mixture of metallic and semiconducting. You see the peak deconvolution. And over time, as you start to oxidize it and dissolve it, you see peak shifts to the left and changes in peak shape. And if you deconvolute the spectrum, you can see you're headed toward the pure 2H semiconducting phase. And optical data gives you the same result. So it seems like this 1IT phase oxidizes faster than the 2H semiconducting phase. And you can actually see that directly by taking the metallic phase, hydrothermally converting it to the semiconducting phase, and then looking at the rate of oxidation and dissolution. And you'll see as you make that phase reversion, they call it, you can reduce the rate at which these things oxidize. So why in the world is the oxidation rate for molybdenum disulfide dependent on this phase? And maybe in biology we wouldn't care, but it's an interesting question for the field. And what we have done is worked with Andy Peterson here at Brown, who does DFT calculations, and he's developed a hypothesis that the metallic phase oxidizes more readily because it's capable of participating in like two-site corrosion type mechanisms. So here's the molybdenum disulfide nanosheet. This is water, and this is oxygen. Water gets oxidized. Oxygen gets reduced on two separate sites. And to make this reaction go further, you need electron transfer between those two sites. And that electron transfer has to occur through the material. That's only possible with the metallic phase and not with the semiconducting phase. And that is our hypothesis for the behavior of molybdenum disulfide. Now, what are the implications? Well, molybdenum disulfide, if you look at its cytotoxicity, it doesn't show a lot up to reasonable doses. And now it's possible that the ions that produced are toxic, but because it takes a month to produce those ions, we don't see that effect. But you can do salt controls and put equivalent amounts of molybdate ion in the system, and you do see tox at very high doses. But this top dose here of 80 micrograms per mil, if you convert all of that to the soluble ion, that corresponds to this concentration. And this material then is non-toxic at doses we would normally consider in nanotox studies. So MOS2 is a nice material. It's both the nanosheets and their soluble products seem to have a low cytotoxicity. And at least for this material, we might also set it aside as a somewhat lower priority case for detailed nanotox studies. But it also has the interesting, opens up the possibility of using MOS2 in biomedical applications because of its programmed degradation. So something that degrades over the course of about a month could be used in various biomedical implants. It can go away over time, and both the sheets themselves and their soluble dissolution products are believed to have low toxicity. So it's an interesting way to, as a spin-off of our work on environmental health, to identify a material that might be interesting for implantable technologies. So those are my two case studies. I want to step back and say that we think these case studies are part of a larger framework, and we're going to put this framework out and talk about it, where dissolution experiments are used as a way, as a first step to sort through the world of 2D materials. And here's how we see the framework being applied. You may have a test material, a 2D nanosheet, and you may start with a literature search, usually using data for the bulk material which is available on its stability and its dissolution pathways. Is it susceptible to oxidation or reduction or to hydrolysis? And based on that, you would select the medium that you would like to study. It could be simulated lung lining fluid, which you would want to keep air saturated if the material was susceptible to oxidation. If it's susceptible to reduction, we would suggest simulated lung lining fluid with GSH addition. And you'd have to replenish the GSH to make sure it doesn't get oxidized by the air or by the material. And if it's a non-redox system, you could use simulated lung lining fluid. And we might also suggest you use phagolysosomal simulant fluid to model the effects of the different pHs, both in the intracellular and extracellular compartment. And based on what you get, you may see rapid dissolution, slow dissolution, or no dissolution. And if it's rapid dissolution, you can imagine that our interest turns away from the solid to the nature of the dissolution products. And this is now a chemical tox question. It's very different. And now what is the hazard associated with these dissolution products? And maybe we know that already from the literature. Maybe we find it out by dissolving the material and doing in vitro studies. But by one method or another, using simple techniques, we could classify this further as either low or high in terms of the hazard associated with the dissolution products. And if you have low hazard dissolution products, we would call this a class D material, biosoluble with low hazard degradation products. And an example of that material would be our molybdenum trioxide 2D nanoribbons. So I think we would call those class D materials, not worthy or not a high priority for further detailed study. Then there's materials that are biosoluble, but they produce toxic byproducts. And we didn't have one of those in our example set, but an example might be nanocopper. Oxidizes pretty rapidly, gives off copper ions, is quite toxic in the lung through the redox activity of the copper ion itself. Has to be treated differently, but I think our attention is better paid to the chemical aspect of the toxicity rather than the particle-specific aspect. And then we have materials that are in between that dissolve slowly, and I think molybdenum disulfide is one of those. And we finally have materials that show no dissolution. Under these conditions, it doesn't mean they're not long-term degradable, but these would be the highest priority materials for more detailed characterization. And one of those would be multi-layer graphene. It's thermodynamically oxidizable, but it's difficult. Kinetics are very slow. And this kind of leads to the last part of my talk, where we now have a material whose solid phase we're pretty convinced is the key to understanding biological behavior, and we need to look very carefully at the nature and geometry of that solid phase. And this leads me to the last part of the talk about physical and mechanical interactions. And this is arguably the most important aspect of the 2D material field at the nanobio interface, is how these shapes interact with cellular structures. And this was a figure from our review article put together by Huajin Gao, our collaborator. And it shows some of the ways that 2D materials have been shown or hypothesized to interact with the cell. Being atomically thin, they can potentially penetrate the membrane with low energy barriers, and so they can do passively. Some people have postulated they can reside in the hydrophobic core of membranes. Some of them are flexible and could adhere conformally to a cell surface. They can absorb things and carry those things into cells. Materials that cut the membrane this way may end up in the cytosol. Multi-layer stiff materials may be taken up by endocytosis or phagocytosis, but then can they be packaged at these unusual shapes inside the cell successfully? These are some of the issues, and I have just a couple of examples in my last few minutes of these mechanical interactions that our team at Brown has worked on. And the first one comes from a few years ago where Agnes in her lab and Annette van den Busche, who was doing many of the experiments, found that these sort of multi-layer graphene flakes that you can buy commercially are taken up by cells, and they're found in the kind of near nuclear space, as you see here, often lying flat. And if you interrupt the process, though, using ex situ SEM, you can see the process of entry, as it's occurring. And instead of seeing invagination here at these points, where the flake is being taken up by endocytosis or phagocytosis, it doesn't look like that. It looks like a more uniform cutting, even where the membrane may be extending outward. And this is kind of a sign for passive entry or cutting of a material rather than active uptake, at least in the early stages. And Hua Jun Gao does molecular mechanics modeling and nanomechanics modeling. And so he put like very small graphene layers above these coarse-grained simulations. These are full membrane sort of molecular dynamics simulations, and these little graphene sheets dip in readily. But if you take, these are large sheets, if you take a large sheet and you try to bring it to the membrane and cut it, and the membrane's undulating and oscillating, you cannot, with low energy barrier, penetrate that membrane. They're repelled away as the membrane undulates. And it's kind of a problem because the data shows that these flakes enter, but the simulation shows that they can't. So that sounds like doesn't make a great publication. So, but it turns out that the resolution has to do with the structure of graphene sheets. These graphene flakes don't look like the pictures on the cover of Science magazine. They've been ripped, essentially, by exfoliation processes from the lattice. And look how irregular their surfaces are. And so if you take an irregular surface and you dip that into a membrane, then you concentrate the force at these tips, it readily penetrates, and once it does, it propagates along the membrane, and you can get passive uptake associated with the irregular shape of the surfaces in graphene nanoflakes. And it's a bit like cutting bread. If you try to cut a piece of bread with a smooth knife, and if the bread were flat and you pushed on it, it'd be very hard to break the crust. But they make bread knives serrated for a good reason, to concentrate the force on tips. The press got a hold of this and wrote some stories that it's a very vivid image, the idea of graphene slicing into cells. And so there was a lot of talk about graphene being toxic as it's sliced into cells. But the article itself is not about adverse biological effects. It was about the fundamental physics of entry. So I think that was somewhat misleading. Don't blame us. But we are, of course, interested in adverse effects. And for 2D materials, a lot of that seems to be associated with the lateral dimension. If you look at very small lateral dimension graphene flakes, they're taken up, in this case, by macrophages easily. And as the lateral dimension grows, it gets more difficult. Even 3 or 4 micron sheets can be taken up. But if you get to very large sheets, they obviously can't be taken up by a single cell, and you get these multicellular constructs that surround the flakes that may be the beginning of a granuloma. And so there's a lot of interest in understanding the effect of lateral dimension. And at what point for a 2D material does the size grow to the extent that it becomes very challenging for cells to process? And it's a bit like the problem with carbon nanotubes, in that these are very thin. So even large flakes can have a small aerodynamic diameter, which is the settling, which governs the settling velocity in the lung, so it can be respirable. But the long lateral dimension makes them difficult to process. And so we became interested in this question: exactly when and at what size do we begin to see challenges to cells associated with the processing of these materials with highly unusual geometries? And my last few slides, it's the last little case study, explores this. It's our most recent paper, and it's not about graphene, I regret to say. It's about carbon nanotubes, and we'll talk at the end about what the implications might be in the world of 2D materials. But Agnes and Annette have studied the effect of a increasing nanotube length on cytotoxicity. And this data shows that if you take a long, stiff carbon nanotube, it's cytotoxic. If you take a variety of particulate forms of carbon, regardless of their shape or detailed structures or surface chemistries, they seem to be non-toxic in this assay. And then we undertook to progressively shorten the nanotubes and see if we could make this toxicity go away. Was it really length dependent? So we did an oxidative cutting process using nitric acid and sonication. And you can cut the nanotubes and do a lot of image analysis and get mean sizes. Of course, you've changed their surface chemistry entirely. So what we did is re-annealed them to restore something like the original surface chemistry. So we have a nice sample set of nanotubes of different length with arguably the same surface chemistry. And you can show the progressive loss of this toxic effect when you go to 1 micron and then a half a micron and down to nothing with the particulate forms. And so there was some reason to think this had to do with lysosomal disruption. And Agnes and Annette have this assay that looks for the release of cathepsin B, which is a protease inside lysosomes. And if a lysosome is damaged, it gets out. This particular protease keeps its activity at the high pH in the cytosol. So it wreaks havoc inside the cell once it gets out. And it's a very important target for these toxicity studies. And this data shows that in an unexposed cell, this cathepsin B remains intact inside all these point-like lysosomes. But in the case of nanotube exposure, you still see the lysosomes, at least most of them, but you see this diffuse glow around them that shows the release of cathepsin B into the cytosol in the near lysosomal region. So this has to do with lysosomal damage, we believe. And Hua Jin's work took these simulated nanotubes and put them inside lysosomes and tried to figure out what was causing the damage. And the simplest idea was if the tube gets long enough, it punctures the lysosome and out come the contents. But in his simulations, he could never make that happen. Instead, the lysosomes, and these are just vesicles really, take on a kind of a pear shape and then a cherry shape. They're happy to conform around the tube rather than be punctured by it. So he's developed a theory that as nanotubes get longer, they're forced to press against the inner leaflet of the lysosome membrane. And as they press, if they're hydrophobic, they begin to extract lipids. And you can get a cascade of lipid extraction from the inner leaflet of that membrane that causes the damage. And so that's our current molecular level theory of how that damage takes place. But it certainly, we know, is triggered by nanotubes that reach a certain critical length. And my last slide is, I think, the best example that we would have to offer of a safe design tool. And it was in this recent paper. And it shows the last part of the study, which is now that we know, or we have a theory about what causes it, exactly which types of nanotubes will do this. And so this plots the diameter of the tubes versus their length. And this is the lysosome size. And so by this modeling, you need nanotubes that are larger than the lysosome in order to begin to put pressure on the inner leaflet of the lysosome. But they also have to be stiff. So these nanotubes, while they're pushing on the lysosome is pushing back. And if they're too thin, they will buckle inside the lysosome. And then they will be stiff fiber-like, and they won't present themselves to this biological system as a stiff fiber. And that's an old mechanics buckling problem. It's not that much different than looking at the beams in a building. And the taller and thinner the beam, the less force it can accommodate without buckling. And so this is the Euler buckling theory. And that line is this thick blue line on this plot. And tubes that lie on this side of the line are thinner or longer, some combination, would be what we call biologically soft. And the force used to calculate this is the lysosomal compression force that we have from the literature. And nanotubes on this side would be biologically stiff. So we're proposing that this regime, where you're larger than the lysosome size and you're on the right-hand side of this buckling criterion, you're stiff and not soft in a biological sense, is the regime where you can activate that mechanism. And we've compared with this plot the theory, which is the blue line and this bar, with data. And in each of these cases, it's colored red. We have a material that has been reported in the literature to activate this lysosomal damage pathway. And all the materials in blue, including all these particulate materials, have been reported not to activate that pathway. And it seems like it works. And what I'm excited about this is it's a kind of a, if you will, a materials engineering quantification, a safe design tool that anyone can use. If you tell nanotube developers that you have to have a biologically soft material, they don't know quite what to do with that. But this criterion is based only on the diameter and the length. Every nanotube developer knows what their diameter and length are. And this is yet to be fully tested, but it's a kind of a quantitative design diagram that might allow you to select a material or make a material that would avoid at least this particular tox pathway, which I think is a great example of a safe design tool. And then I guess I'm done, but I would like to say back to the 2D material theme, I think a lot of work could be done for 2D materials, which some of them are floppy, Some of them are stiff. They come in a variety of sizes. Is there such a phase diagram or a safe design tool that's quantitative that could be put together that would explain for all of these materials under what conditions of geometry, under what thicknesses and what sizes do we expect adverse effects associated with these mechanical interactions? That would be a great goal for the next few years for the 2D material field, as it's generally applicable to all of the materials. Thank you very much.
Well, for a wonderful and interesting presentation. We have time for questions, first from the audience.
Thank you for the presentation. Very, very exciting data. I have a question regarding the dissolution of the materials that you showed. Have you looked into, or is it even possible, when you dissolve these materials selectively, to change either the band gap, so you bring them closer to the redox potential, so the material starts not to be toxic based on redox, but it ends up to be, or similarly, to make the edges of this material more jagged and more sharp, so it can actually enhance the uptake of the materials. Have you looked into that?
Thank you for that. You know, we have not done a lot of characterization of these intermediate half-dissolved products. I mean, both the things you say would certainly be possible, but we have been focused on geometry and the rates, and we haven't looked. You see jagged edges appearing sometimes in materials if they're originally smooth, but we haven't considered the things you're asking. It would be a nice addition to the kind of work we're doing.
When you see the dissolution of the nanomaterials, do you actually see the reduction in size, in time of the nanomaterials?
Yeah, it possibly. Although, you know, if you have a very polydispersed material, it can be complicated, and dissolution can cause the little one leaving the big ones behind, so it can seem like they're getting larger. But in the case of molybdenum peroxide, because the whole thing happens relatively quickly, we have quite a set of images, and there you can begin to get a sense for how dissolution occurs. And it seems to involve thinning, for that material at least. It's thinning and shortening, then eventual breakup. But it's a complicated question how a size distribution of anything evolves under the case of, say, surface area mediated attack, especially if it happens on certain facets. It's a whole topic in its own right.
And my second question is, like, when you see the graphene penetrating the membranes, is it like monolayer or is it multi-layer? Because to me it looks like multi-layer.
This, right. We haven't done a lot of work with monolayer graphene, and partly because, and I just my own opinion about this, but people use CVD to grow monolayer graphene on, say, on copper, and they transfer it to silicon for electronic applications. But it's a little hard to serious exposures in those kind of scenarios. We took a full wafer, a full industry standard silicon wafer, and you can cover it with monolayer graphene and scrape it all off. You can't get enough to do a single tox experiment. Plus, it's bound to the substrate. So our focus has been on these graphite exfoliation products, so poor man's graphenes, if you will, but they're important. And so this study was done with graphene nanoplates, which was supplied to us by a company we work with. And we have a set of them. Some of them are as thin as the ones you're working with, 3 or 4 layers, and some of them are up to 20 layers. And so they're not really atomically thin, but they do have these sharp edges, and their edge structures have points that are quite thin. And the simulations, some of them are on monolayer graphene, but some of them also used multi-layer graphene in the simulation. And the energy barrier goes up as the edge gets thicker, there's no doubt. Single-wall nanotubes are thought to enter membranes passively, right? And they're about, they're several nanometers in size. So you can have some multi-layer character to graphene sample and still have a relatively small energy barrier for penetration of the membrane, as long as you don't try to take the entire length of a uniform edge at the same time and penetrate. It makes the energy barrier way above.
Thank you very much. Very interesting work that you're doing. I have a question regarding the oxidative degradation of the materials. You showed the example of molybdenum disulfide, that it can degrade based on the metallic versus the semiconductor properties. carbon nanotubes and graphenes also have the metallic and semiconductor properties depending on its structures. Do you believe that this functionality will also be useful there for degradation of those materials inside biological systems? Because right now what we have the understanding is that is the surface properties like the oxidation versus the pristine material that is responsible. So if you can give some brief idea.
So we haven't tried generally to correlate pollution with electronic properties of metals. There's probably some relation there. But for this particular material, we just found that the two phases were different. And to explain it, we first thought that it was easier to form the oxide on the metallic version. But in Andy's calculations, that didn't prove to be true, so we came up with this corrosion mechanism. But for the other materials, we haven't necessarily taken that approach. You can do thermodynamic calculations that will tell you whether something's susceptible to oxidation. Graphene is, it goes to CO2 with a very, very negative free energy. It's a question of kinetics. And you know there's a body of literature. You can't oxidize graphene with molecular dissolved oxygen over any kind of time frame. But ROS species can attack it. And there's been quite a literature on enzymatic degradation. So these are, especially the multi-layer materials, they're quite durable. There's some argument still over whether over time such a material, in the presence of the right enzyme, ROS generation, could be slowly degraded.
Thank you. My question is the same as Kunal asked about the molybdenum disulfide. When you give the case study, it occurred to me to look at the band gap structure again. Can you please go back to the graph? Yeah. DFT study that shows that the water can be reduced and then oxidized on top of the molybdenum disulfide. So I was wondering if it's matched with the band gap structures of the molybdenum disulfide or not, because so it graph maybe.
Yeah, we haven't necessarily. It's a good question. We haven't necessarily tried to correlate the oxidation activity using this theory. This theory has more to do with whether electrons can go in and out associated with these biological redox methods. So the theory that there's some relation that you're getting at, certainly. But the theory we've been using for oxidation is this one, really, which is it doesn't use the actually not based on the band gap, because for the bulk materials at least, you can calculate the thermodynamic potential for oxidation by writing out the stoichiometric reaction. These aren't the nanosheet versions, but it gives you have that couple, so it doesn't directly edit in the data in some way, but we don't directly use the.
My question is that did the DFT theory confirm that the positively charged on the surface delocalize the positive charge on the surface of the molybdenum disulfide, or you didn't look at?
Oh, yeah, thank you. I'm not sure I can answer that. And we never asked Andy to, and I don't know if it's even an input in his calculation, what like the surface charge you would see in a colloidal suspension. So, yeah, I don't know if he sees that or uses it in his calculation. I'd have to ask him. He's the expert.
Instead of small platelet particle sort of things. So have you looked into the effect of morphology or more sort of edge to the surface ratio on the dissolution pattern of these materials?
No, some people, is this molybdenum trioxide? Oh, so you're
Yes.
working. No, we haven't. I know there's a lot of work done on silver because it was such an important compound. And some people have, Peter Vixland, I know at Virginia Tech, had done some kind of work looking at growing little islands of silver and looking at how the shape evolves and which facets are. We haven't What we have is what you've seen, and so we haven't.
I was thinking.
I would imagine, right? Certainly, I'm sure those oxidation reactions occur preferentially on some facets, but we don't have that data.
In liquid, some sort of a stabilizers, right? So can you comment on how the presence of the stabilizer can change the electronic structure and eventually maybe the dissolution?
Yeah, that's a good question. We haven't, with the carbon world, we're dealing with materials that have been thermally or chemically exfoliated. We don't use mechanical exfoliation. I know in your lab, you guys have pioneered that in part. We do a sonication-based mechanical exfoliation to get MOS2. But we have never studied, I'm sure adsorbates modulate the electronic property. We haven't studied it.
And the last question. Who are actually studying as the buckling more sort of the surface chemistry, which is manifesting itself in a stiffness?
The theory that we're using does not have surface chemistry in it. It's the Young's modulus, and it's the diameter, it's the length. It's a beam theory. It goes back to way back, and so some of the multi-wall tubes that are stiff, they're 40 nanometers in size, but you all I know in your lab work a lot with single wall nanotubes where you have one wall, and I can imagine that surface chemistry, if you modify it, could have a big influence on the effect of the modulus. I think the effect would go into the modulus in that theory. And so most of our materials are, I think, too large for that to be a first-order effect. I could be wrong. Single-wall nanotubes, they're kind of outside that paradigm. They're so small, so thin, and floppy, not even long enough for the most part. So what I find interesting is people talk about high aspect ratio being a problem, is some single-wall nanotubes have enormous aspect ratios, but they can't present as stiff fibers because they're outside of that buckling theory. So this is a theory that more identifies the fiber-like, thicker materials as pathogenic.
I know that you've worked with graphene platelet-like graphene sheet. Would have a different penetration sort of the behavior compared to a crumpled one, which the SP2 sizes are, the areas are more exposed to the, cell wall or something.
Properties of the graphene oxide versus graphene. There's some differences, like in tensile strength, but there are also some similarities. And I think crumpling can certainly provide entryways for cell uptake. We've seen graphene goes into cells, pretty well, but so do the flakes, and we haven't studied the differences in detail.
We have two questions from online. The first one is, do you have any examples of case studies regarding the toxicity of nanomaterials in food?
Answer that very simply. No, I talked to Phil. We've not studied food. We've not. It's an interesting research area, though. But we have nothing to. And so we haven't. No, we've not something that we've expert at.
And the other question we have from online is, would you have any comments on how the range or size distribution of the layered materials based on different exfoliation methods could impact the colloidal properties and dissolution?
Yeah, we haven't studied that either, but so dissolution, of course, is surface area dependent as a first order term. And so there's no doubt that the finer the material it is, the faster any dissolution process to be. And like with molybdenum disulfide, since it takes a month or something to dissolve, it could make a big difference, the size of it. And people, some aspects of that. Molybdenum disulfide, when it oxidates, It usually oxidizes from the edge or at defect sites that widen. It doesn't oxidize, through the thickness, as you can imagine. So it's probably edge-mediated. And for the small lateral dimension, the shorter the distance you have to go through to slowly oxidize and dissolve the material, one could imagine that the overall fineness would be an important variable, and there could be also shape-dependent effects, as was mentioned by a previous questioner, but we don't have data on these things. Certainly size is important for dissolution kinetics, most certainly.
Bob, for the wonderful presentation and for coming to give the talk. Thank you all for joining us.